Hello, I'm Xiaobang. I'm from Uvascular University. I'm currently working as a project researcher. Today I'm going to talk about my project on this. First, let me introduce AIQUSEC project. This project is part of Business Finland Digital Trust Program and part of Nokia WaterLOOP program, which aims at creating a competitive edge for sustainable future networks. The goal of the AIQUSEC project is to make measurable advances in cybersecurity for access and edge services and operational technology. The project integrates novel quantum-safe, AI-based and device-level hardened and scalable cybersecurity solutions. Cybersecurity is an essential part of all themes in the program, and no goal can be achieved without sufficient cybersecurity solutions in place. GYU and Savonia will work together to research cyber threat profiles for edge devices used in water utility and smart factory environments. Specifically, GYU will collaborate with Savonia to integrate relevant components of Savonia's IT and OT system with GYU's security assurance and validation. Additionally, GYU will coordinate and offer guidance for proof of concept related to critical infrastructure applications. The use cases involve data gathering and analysis in 5 phases: identification, collection, monitoring, analysis, and decision-making for countermeasures. Speaking of cybersecurity in water utilities, cyber attacks against water infrastructure have been increasing over the past decade. Taking out critical national infrastructure has become a top priority for cyber criminals. All water distribution and treatment systems are at risk. It is important to develop real-time detection schemes that help protect these critical infrastructures. Traditionally, the supervision of OT system has been done by system monitoring experts who establish normal behavior threshold for every measurable sensor output. If a measurement exceeds its expert-defined threshold, then it is considered that the system is not behaving as expected. Given the size and the complexity of today's operational system, the number of sensors has increased dramatically, making traditional expert-defined monitoring process slow and vulnerable to errors. The automation of OT system monitoring has become a necessity. Therefore, we want to utilize AI models to cope with decision-making process in a real-time and a scalable way. For the past year, I have been working with Savonia WaterLOOP to develop AI-driven approaches for WaterLOOP monitoring. Detecting unexpected behavior on a set of correlated measurements over time is an active research discipline called anomaly detection in multivariate time series. Many approaches have been developed to address this issue. Most commonly used techniques are distance-based, such as k-nearest neighbors, k-means, SVM. This method first uses a distance measure to quantify the similarity between objects. Objects that are distant from others are considered as anomalies. However, as the number of dimensions increase, these techniques generally suffer from underperformance due to the curse of high dimensions. Recently, unsupervised anomaly detection methods based on this deep learning have received a lot of attention among deep learning methods. Prediction and reconstruction-based methods are very popular. Prediction-based methods such as RNN and LSTM learn a predictive model to feed the given time series data and then use that model to predict future values. A data point is identified as anomaly if the difference between the predicted output and original input exceed a certain threshold. Reconstruction-based methods like autoencoder learn a model to create a synthetic input by mapping the original input to a lower dimension space, then back to a high dimension space. This method assumes that anomalies lose information when they are mapped to a lower dimension space, and therefore cannot be effectively reconstructed. So high reconstruction errors suggest high chances of being anomalies. We can generalize these deep learning-based anomaly detection approaches into a modular framework. In the first module, we load multi-channel time series data from sensor recording datasheet, which is normal behavior data. Next, we segment time series data into window sequences as training input. We also use min-max scaler to normalize the input data. Then in the training phase, we feed the training data into the deep learning models to learn the pattern of normal behavior data. In the post-processing module, we use the learning model to generate expected time series data. Then we calculate the error between the expected output and the original input on the test dataset, which has anomalies. We use anomaly percentage in the test dataset to determine a threshold to extract anomalies. So far, we have tested 5 advanced deep learning models on WaterLOOP dataset. We use precision recall F1 scores as metrics to evaluate the performance. In comparison, COTA achieves the best result, and we attribute the superiority of COTA to the contamination tolerance and uncertainty modeling. The monitoring task in this project so far is focused on anomaly detection, which identifies time points during operation where sensors indicate anomalous behavior. Next, we are going to find out the specific sensors that malfunction, which would help the operator verify the anomalies and take corrective action. We will also extend anomaly detection use case into a smart factory scenario. We will explore the effective method for the smart factory dataset. So, that's all. Thank you for your attention.